Welcome folks to this new tutorial to learn how to use the Cadence IC Tools. And this is part 4, and in part 4 we're going to learn how to use OpAmps, basically by porting components from a provided library, and how to use the AC sweep. It is basically we are going to sweep or vary the frequency of the system, and then we would like to measure the frequency response for the circuit or the system. So let's get started. I have already logged into my account. So the first thing I'm going to do is I'm going to open N terminal. And now I'm going to move into the Cadence tool. So I have already used this command before, so I'm gonna move to this specific directory where it is called the home directory /class /ee311 /cadence, and this particular command have been used before, so I used the upper arrow to do that. I'm gonna hit enter, and then I'm gonna run the Virtuoso software, or the Virtu software. Basically I'm going to also use the upper arrow twice because I have already used the software before. Now I'm going to hit enter, and it should be ready now to load the software. So as you can see, the software have been loaded. So now we still gonna load the environment. Here it is. So the first thing we're gonna do is we're gonna add a path, a library path. Basically we're gonna come into tools and we're gonna click on library path editor, and here is the library path editor that we are interested in. I have created the library here. I called it ideal, and so I entered it in. So what you do is you can click on one of those, you can give it a name. I use the name ideal, so you can use the name ideal for it, and then the library path should be under wherever you have connected the Cadence tool at. So in our PC that was /net /IC Tools /Cadence, and then you're gonna use /IC 616 /tools, and then we're gonna use /DFII, where the II capital letters. Then we're gonna use /samples, and then /artist, and then we're gonna use /AHDL in small letters, and then capital LIB stands for library. So it is the AHDL library that is provided to us when we installed the Cadence tool in our server. So if you have a different path, check with your network administrator to tell him where is this library is located, and that's the path you need to enter. Okay. So if you type the library here and then hit enter, and that should work. And once you hit enter, then you need to save it. So go ahead and save. And once you save it, now you can exit. So let's go back one more time. Go to tools, click on library path editor, type the path location of the AHDL lib, and I gave it a name ideal. You can give it any name. Basically it is the AHDL library. It is to some extent a behavioral library because it uses some language like Verilog to describe the behaviors of the circuit. So this library is a behavioral library, which is a little bit different than what we call components type of libraries, where you add resistors and capacitors and so forth. This library is a behavioral library. It is basically a software that describes the behavior of the circuits. So once you write the path, the location of that library here, then click save, and then do exit. So what this will do, basically this will enable you, when you add instances, when you add components, to go back to this library and board its components. So it isn't just a reference library, but it is a library that you have access to directly, and that's basically what do we mean by that. So now what we're gonna do is we're gonna go to File, just like we did before. We're gonna add a new library that's basically for homework number 3. So we're gonna say File, a new add library, and the new library gonna be named homework, and I'm gonna do _3, stands for homework number 3. And then we're gonna select reference existing libraries, apply, and over here I'm gonna select the analog library to be added. Okay, we already added it, so that's it. Cancel. So we already added it now, that's why we clicked on cancel. Now I'm gonna do a new cell view. That's basically the circuit, and then this circuit under the library homework 3, we're gonna say the circuit gonna be OpAmp circuit 1. So it's gonna be OpAmp circuit 1, and make sure that the application gonna be the ahdlLib tool. You can click on always use this platform. So sometimes it catches it, sometimes it doesn't. Anyway, so you need to make sure that you have it. And now we are interested in adding the circuits to the schematic. So the first thing we're gonna do is we wanted to add the OpAmp. So to add the OpAmp, I'm gonna come in here to create instance, and I'm gonna click on it, and we're gonna go to browse to select the library, and you see here we have the library ideal. That's the library I want, which is the library that have been added to the path. When you click on it, you're gonna see a bunch of elements here. So one of the things I'm interested in gonna be the OpAmp, which you have it over here, so you can see it. I'm gonna click on it. When you click on it, now come to the properties for it. So I'm gonna enter some values. Those values are similar to the OpAmp 27 data sheet. So the OpAmp 27 is one step above the 741 OpAmp. It behaves nicer than the 741 OpAmp. So we're gonna call it OpAmp 27. You can give it _1. And now we're gonna enter the values for the OpAmp. Keep in mind that this is a behavioral values. Those are behavioral components that we need. I'm interested in what's the gain is, what's the unity gain bandwidth, the frequency at unity gain, what's Rn, what's Vn offset, what's I bias, what's the slew rate, what's Ro, and the other ones I'm not interested in. So the gain gonna be 1.5 meg, and meg gonna be capital letter M. Capital letter M stands for meg. The small letter m means milli. The frequency, the unity gain frequency is basically gonna be 8 meg, and Rn gonna be 4 meg, and Vn offset I can use 30 micro. So U stands for micro. We're gonna say 30 U, which means 30 micro. The input bias current going to be 15 nano. The slew rate, we have it to be 8 meg, and our out going to be 70 ohms. Those are the parameters that we are interested in to define the OpAmp, the 27 OpAmp, which will make it behave near the one that we use in our labs. In our labs, we use the 27 OpAmps, and those parameters will make this OpAmp behaves almost similar to the ones that we use in the lab. Now keep in mind that we are using the typical values here, so you still need to add the minimum and the maximum values and all that if you want it, but that is a different type of simulation that called Monte Carlo. So Monte Carlo simulation will tell you what's the deviation of those parameters going to be and how will it affect the circuit. We are not interested in that at this point. So that's all what we need. Now I'm going to place the OpAmp over here. So let's place it over here, and I'm going to click escape so we can cancel everything. Let me maximize this window because that's what I'm interested in, and I'm going to zoom in to fit so you can see it. This is the OpAmp. Now the OpAmp will have non-inverting input, inverting input. It will have the positive power supply. It says V supply P, the negative power supply V supply N, the V reference, and that's the output. And it has entered all those parameters that we wanted that defines the OpAmp. The most important ones used here or shown in here is what's the gain is, what's the unity gain bandwidth, and what's Rn. Those are the most important parameters that affect the behavior of most OpAmps. The other ones can be avoided. The slew rate is also extremely important, but it also relates to the unity gain bandwidth. So those are extremely important parameters. In any case, we are interested in adding the power supplies. So the power supply is going to be two DC voltage sources. We're going to have one to be plus 12 volts and the other one going to be a negative 12 volt. So I zoomed out a little bit. Let me zoom out even a little bit more, and then I'm going to move this one a little bit to the top like that. Now I'm going to add instance, and in this instance now I'm interested in adding VDC. So I'm going to change from ideal to ahdlLib, and over the cell here we're going to say VDC, and when we do that, this is what we have, VDC. So the first one going to read a value of 12 volts, the DC voltage, and that's all what I need. So DC voltage will read 12 volts. So I'm gonna place it over here, and I'm gonna hit escape, and now I'm gonna add another instance, and the second one we're gonna add the voltage to be negative 12 volts, and I'm gonna call it VEE, and we're gonna place it over here. Let me correct the name of this voltage source. So I'm gonna click on it again, and then I'm gonna hit the letter Q, so it gives me the property. So the instance name, I'm gonna call it VCC, just change it to VCC. We're gonna hit OK. So now the name have been changed to VCC. So if you wanted to change the property of anything, just to click on it, and then, or double click on it sometimes, and then hit the key Q, the letter Q in your keyboard, and that will open the properties for you. So we don't need to do anything for the OpAmp. And this one here, let's click on it and then do Q. So you can see that it's a 12 volts. So let me fix that also here. That's error. It's a space V. And this one here also, yeah, so that's correct. Okay, so we end up adding the two voltage sources. So now what I'm going to do is I'm going to zoom out a little bit, and I'm going to move this to the top over here, and now I'm going to add grounds. So let's go back to add instance, and under add instance I'm going to do browse, and the cell going to be ground. So ground going to be GND. From previous tutorials we know that. So I'm going to add one ground here and another ground here, and now I'm gonna connect this voltage source, the power supply, to the positive end like here, and the negative power supply to the negative voltage source. So basically what we did is we created a 12 volts power supply and the negative 12 volts power supply. We connected the positive 12 volts to the positive power supply end and the negative 12 volts to the negative power supply end. Now what we're gonna do is we're gonna add two resistors. So we're gonna add the 2 feedback resistors. So we are under analog library, and now we're gonna add the cell called res, stands for resistor, and the first one gonna be a 1k ohm resistor, but I need to rotate it. So when I rotate it, I'm gonna add it over here, and I need to add one around the feedback, but the one around the feedback I want to make it 10k. So I'm gonna hit escape, then you add instant, and it has 10k, and do rotate, and we're gonna add it over here. I can change the names if you want it, or if I want to change the values of the resistor or anything, just click on it and then hit Q, and here is the values for it. So it's called R1. I can make the name for it R2, and the value is 10k. Then we're gonna say OK, and then for this one I'm gonna click on it, hit Q, and change the resistance name to be R1. You can do that. So it's R1 and R2. Now keep in mind that the Cadence tool will start with R0, R1, R2, and so forth, but most textbooks will call this resistor R1 and this resistor R2. Now what we're gonna do is we're gonna finish connecting those resistors around the OpAmp. So this resistor will go from this end to this end, and then this one will go from this end to this end, and finally this output will go back to this resistor over here, like that. So this amplifier going to be non-inverting amplifier. So the first thing we're going to add now is a sine wave as input signal. So we're going to go to browse and add instance, browse, and under cell we're going to add a sine wave. So we're going to call it vSine, and vSine is shown here. So we're going to click on it, and when you click on it you have some properties we need to enter. So what we are interested in is the amplitude of the sine wave, gonna be 0.1 volts space V, and the initial phase gonna be 0, and then the frequency we're gonna have 1000 hertz, and that's what we're gonna use. So we're gonna replace this somewhere over here, and now we're gonna also connect this sine wave into the non-inverting input of the OpAmp, and now we need to have a couple of grounds, and we're almost done. So we're gonna add grounds. So we're gonna add instances, and then here under cell in the analog library we're gonna do GND, and that's the ground. So we're gonna add a ground here, we're gonna add a ground here, and there is another important ground gonna be the VREF. The V reference is gonna be ground. So let's just move some of the things to make sure they are connected. This ground is connected, this ground is connected, and let's just see if it's connected, and let's see if that is connected. So yep, everything is connected. Now there is one more thing we need to add, is basically the ports. So add pin or port. So we're gonna add a pin, and in this pin we're gonna say it's input output, and the first one we're gonna call it V out, and V out gonna we're gonna place it over here. And there is another one we're gonna also place over here. So let's do that. We're gonna call it VI. So let's connect VI. So VI gonna come from this node to this one, and then from here to V out. I believe that this is everything we have done to do the schematic. So what we're gonna do is we need to save and check, or check and save. So let's check the circuit and save. We need to click on it, check and save. So it says there is one warning. Let's see what's the warning was. So I believe there, let's see if we gonna do it again. There is one more warning found. Ah, it's over here. Okay, save and check. Okay, so what I'm gonna do, let's see if we can simulate the circuit. So we're gonna choose transient, and this basically says that the frequency is 1000 Hertz. So we're gonna run 10 clock cycles. So we're gonna make the stop time to be 10 milli. So that is the stop time for our simulation. Make sure that you click transient. The stop time will be 10 milli, which will give us 10 clock cycles. And make sure that you enable the simulation. Let's click OK. Now we're gonna set the outputs. So to set the outputs, click on this icon where it says set outputs, and then we're gonna click from schematics. We're gonna click on VI and on Vout, and then I come here and I say setting outputs. You can see that we added VI and Vout. You're gonna do OK. And now basically it's done. We defined what's the simulation is by choosing the analysis. We defined what's the output's gonna be. Now let's run the simulation and see what do we have. So you can see that the sine wave at the output is not very nice. The reason is that we haven't requested to use a very high resolution. We have used basically a coarse simulation resolution. So we need to come back to make it look nicer as a sine wave. Go back and click on choose analysis, and here where we said that the accuracy default, we're gonna use conservative, and that will make it a very nice sine wave at the output. But that usually requires more time. Since this is a very simple circuit, the simulation gonna be roughly fast, so we wouldn't even worry about that. So go ahead and click on conservative to give you a very nice accuracy. Click OK, and now let's run the simulation again, and we should see that the output should have a nice sine wave. So again, as you see here, we have a very nice sine wave. If you're gonna go back and make the graph maximize, that's what we have. This is Vout, this the green light, the green line is Vout, and the red line is Vi, and you can see that Vi will go roughly a peak value of 100 millivolt, while the peak value of the output gonna be roughly 1.1 volts, which is what we expect is a gain of 11, because the gain of the non-inverting amplifier is it is 1 plus R2 over R1, and we know that R2 is 10K, R1 is 1K, so the gain is going to be 1 plus 10, which is 11. So here we have a gain of 11, and that was what we have. Now I'm going to close this. And now what we're gonna do is we want it to run AC sweep. So AC sweep basically says that by changing the frequency of the input signal, what's the output going to be? We call it AC sweep. So before we change the simulation, before we change the analysis and make it AC sweep, I'm gonna click on the sine wave and then hit Q, and that will enter the properties page. So one of the things I'm interested in is something called AC magnitude. So this is basically small signal analysis. So the AC magnitude, we're gonna enter it to be 1 and the phase to be 0. So basically the input signal gonna start with a magnitude of 1 and a phase of 0. I entered 1 here for a very important reason. Is basically if this is 1 volt, then the output voltage is going to be the gain, right? Because the gain is basically V out over VI, and VI is 1, then V out is the gain. If you make the input signal to have a magnitude of 1 AC sweep, then the output going to be the gain, right? And that's a very nice trick that we can use. So that's all what you have to do to make this input signal have an AC signal. So this is extremely important point to stress here, is many students, they think that AC means sine wave. Now, and that is true for in most cases, but when it comes to SPICE simulation, B-SPICE simulations, AC means that the voltage is varying as a function of frequency, or the current is varying as a function of frequency. It's the frequency response. The AC magnitude, when you come here to the voltage source and you look into the properties, the AC magnitude, that is the frequency response magnitude, which is different than the amplitude of the sine wave. Okay? So that's a different analysis than this one. So make sure that you understand those concepts. So now, instead of using transient response, we're going to use the frequency response. So I'm going to come here and I'm going to click on choose analysis, and I'm going to disable the transient. So basically I'm going to disable it. I don't need transient. I'm going to do AC. So when you click on AC, make sure you enable it. And now we're going to measure or sweep the frequency. That's all what we're going to sweep. This is the frequency from start to stop. So I'm going to start from frequency equal 1 Hertz to frequency equals, let's choose 10 meg. And then at the sweep type, we're going to say that's going to be logarithmic. And here we're going to define the points per decade. That basically means the resolution. And here I'm going to add 1,000 points per decade. So the points per decade will be the resolution. Basically it says how many iterations or how many calculations or how many points we're going to calculate in every decade as we sweep the frequency. So that's all what we have to do here. You're going to click OK, make sure it's enabled, click OK. So we've chose the analysis. We're going to make sure that setting the output is valid. We should have it from the transient analysis. So let's click on it and you should see that VI and V out. Those are the output parameters that we're going to use. And those are basically voltages. As you can see, this is voltage and this is voltage. So I'm just going to click cancel. We already have it. I'm going to save and check. So we saved and checked. We have one more warning. It has to do with this pin here, so which we're going to ignore. Then you're going to say close, and now we're going to run the simulation. So we're running the simulation. As you can see, the server is running the simulation, and it's a little bit fast actually. I'm surprised. So when you see here the response of the system, this is the input voltage. It's a flat. VI is a flat. In fact, that I don't need it. So I can delete VI. I can click on this icon, if you want to call it, or in this field where it says VI, and I can delete it by clicking the delete button. So all what I have now is V out. So V out will read roughly around 11 volts. You can see it reads 10.99 volts at some frequencies, and here as I move along the line you can see what's the frequency is, right? So you can see here I have about 11. So I'm gonna look around when the gain gonna be 7.77. so when the gain gonna be 7.77, that is roughly over here, and you're gonna have the 3 dB frequency gonna be at 722 kilohertz, right? So over here we were able to have the AC sweep, or basically the frequency response of the OpAmp circuit as a function of frequency. What's interesting is, this is what I wanted you to see from this simulation. In this simulation, as you can see, we don't have any capacitors or inductors in the circuit. We have an OpAmp. We powered the OpAmp with DC voltage sources, and we have two resistors, R2 and R1, that will go around the loop, right? You know, a typical non-inverting configuration. However, when we did the frequency response of this circuit, the gain of the circuit has behaved as a function of frequency, such that the gain dropped at very high frequency. So this circuit doesn't have any capacitors or inductors, but the gain dropped as a function of frequency because the op-amp itself behaves as a function of frequency. And the reason is, internally inside the op-amp there is equivalent capacitances that are used. So sometimes we put capacitors in the op-amp to make sure that the op-amp will be stable in a feedback system. So we add those capacitors. We call them frequency compensators or frequency compensation circuits, as we add those capacitors inside the op-amp to make the op-amp stable. All what we learned in this computer simulation is basically how to add a path for our library, and we were able to port in an op-amp. This is called behavioral model of the op-amp. We entered the parameters that describe the behavior of the op-amp. We got those parameters from the data sheet. We were able to build a non-inverting amplifier. We ran transient response, and we looked at the gain at 1000 Hertz when we applied an input signal, which was a sine wave. And then we end up having an AC sweep, which is basically a frequency response of the circuit, and that is by varying the frequency of the input signal from 1 Hertz to 1 megahertz to 10 megahertz. And we realized that this op-amp, or the entire circuit, behaves as a low-pass filter. So this should be the end of the tutorial, and this should be basically good enough for us to say that we can use ORCAD IC design tool to simulate even op-amps the way we do them in junior year electronics or in basic circuit theory. Now keep in mind that this tool is also used for advanced IC design, but we are really ramping up and we are starting from the most basic circuits. I hope this tutorial was helpful to you, and you should be able to do the homework if you are a student of mine. If you are somebody who is learning how to use Cadence IC Tools, I hope this is also helpful to you. And as we go through the tutorials, I hope that you will enjoy other videos as well. Thank you so much for your time, and I wish you all the best.